Alright, so I'm going to keep it going with 11.1. So let's take a look at a second order differential equation. It's this one, and this is still one that we would know how to solve. Like we would write r squared plus 4 equals 0. Yeah. But we're going to do this with power series. And so we're going to do what we did on the last example, and then we're going to identify the solutions as elementary functions using the ones on our list. And we're going to find our radius of convergence. I'll have to tell you what that means. But let's just start. Assume y has a power series representation like this. So y prime is, whoops, I hope we're not too blurry. So y prime is this, right? And remember, we instead of starting at 0, we start at 1. Whoops, and this should be n minus 1. Just remember, your smallest power of x should be x to the 0. We don't write x to the negative 1, x to the negative 2, anything like that. So actually for this one, when I'm about to do y double prime, so let me write the thing inside first, n times n minus 1 x to the n minus 2, right, because I'm just taking a derivative. I bring the n minus 1 down and I reduce the power by 1. But now n should start at 2. Each time you take a derivative, you basically drop the x to the 0 term. Like the x to the 0 term would be n equals 1 here, and that gets dropped here. And then here, the lowest power is again x to the 0. Anyway, we plug this into our differential equation. So, this plus 4 times this equals 0. I would like to combine these two series. I would like them to have the same power of x. So I'm going to shift indices again. And remember how that works. I bump n down here, like the values of n get bumped down, and they get bumped up here. So I would like to bump this so that n minus 2 becomes n, so I'm going to bump it by 2. So these values go down by 2. So n is now starting at 0 and going to infinity. These all go up by 2. So now I'm like that. Okay, now I can combine these two. The series are summing over the same values of n. I can make this like one big thing. By the way, I'm taking this 4 inside, and I'm doing this plus this, so this is going to be like, yeah, let me just notice both of these have an x to the n, so I'm going to factor x to the n out of this. Other than that, I have c sub n plus 2 times n plus 2 times n plus 1 plus 4c sub n. And this is still supposed to equal 0. And by the way, this 0 I can think of as also being a power series. It's like 0 times x to the n. What I'm getting at here is now I'm just equating coefficients. The coefficient of x to the n here equals the coefficient of x to the n here. Yeah. So what we can do is we can find a recursive formula. If I can solve for c sub n plus 2 in terms of c sub n. So I would subtract this and divide by this, so I would get negative 4 over n plus 2 n plus 1 c sub n. So let's, we'll call this my recursive formula. I'm not, usually I put a box around my answer, but this is not my final answer, of course. So what can we do with this? We can start solving for specific coefficients. So this tells you what a specific value is in terms of the value 2 less than it, like it tells you n plus 2 in terms of n. So this formula isn't going to tell us C0 or C1. In order to find C0, I would have to know C of negative 2. And in order to find C1, I would have to know C negative 1. So those are just whatever they are. I can start using this formula at C sub 2. C sub 2, this is like, I guess, n would be 0, right? So this is like negative 4 over 2 times 1, C0. So C2 is negative 2 C0. C3 is what? This is like n equals 1, so this would be like negative 4 over 3 times 2, C1. So that's negative 2/3 C1. C4 is what? Let's try to find a pattern here. C4 is negative 4 over, and I guess n is 2, so this would be 4 times 3 times C2. And then I can replace C2 with what it is, right? But let me, because I'm trying to illustrate a pattern here, I'm not going to replace C2 with this. I'm going to replace C2 with this, like what it was before we simplified it. This will tell us more what the pattern is. Oops, I forgot the C naught. Right, so see what we got was, I've got negative 4 squared, 4 times 3 times 2 times 1. And let me, I don't want to go too fast, I'll do one more that way. Let's do C5. C5, this is like n would be 3. So I get that. And then I can replace C3 with what it is. But again, I'll replace C3 with this. So I get negative 4 squared over 5 times 4 times 3 times 2, which is just 5 factorial, right? 5 factorial would have a 1, but multiplying by 1 doesn't do anything, so it's the same. Yeah, and this pattern keeps going. So let me, maybe I'll, yeah, okay. Maybe I will do, what should I do to really illustrate this? Let me do just one more, I guess. C6, I'm using this formula, and I guess n would be 4, so I would write -4 over 6 times 5 C4. And then I can replace C4 with this, which is -4 squared over 4 factorial C0. And then what is 6 times 5 and then 4 factorial? That would just be 6 factorial. Yeah. So that's what happens. Every time you do a new one, you get two new numbers on the bottom that sort of go together with the factorial from the previous one, and it just makes a bigger factorial. It makes a, like, 6 times 5 and then 4 factorial. That makes 6 factorial. So the pattern is, right, it's a different pattern for evens and odds, first of all. Right, like C6 has a C0 in it, C5 had a C1 in it. So this is different for even and odd numbers, so let me do even numbers first. So C sub 2n, what does that seem to be? Well, I can sort of guess the pattern. -4 to the n, because I guess for when this is like when n is 3 over 2n factorial times C0. And then what's an odd one? Like, maybe I'll look at C5. I get a power of -4. This would be, I guess, when I'm doing C5, that would be like when n is 2. So I get -4 to the n over 2n plus 1 factorial C1. Right? So what we have here, so actually, maybe I shouldn't be using the letter n here, because it's not really the same as these n's. Let me change all of these to m's. Doesn't really matter. Okay, maybe that's better. So y would be this. And I want to break this sum up according to the evens and the odds, because like we've been discussing, these give different answers. So let me do the sum. Here's all the evens, and I'll do the sum from m equals 0 to infinity of, here. I don't want to go too fast. I'm just splitting the evens and the odds. This covers all the evens from C0 x to the 0 all the way up. this covers all the odds, starting with C1 x to the 1, right? Because when m is 0, this is C1 x to the 1, and going all the way up. So this is all the evens and even powers of x, and these are all the odd powers of x. And now I can just replace them. So this is this, and this is a constant, so I'm going to pull that out. -4 to the m over 2m factorial. Similarly here, I can replace this, and C1 is a constant, so I can pull that out. Okay, so we found, in some sense, this is like the solution to the differential equation. It has two constants, which it should. You know, typically, when we're talking about the solution of a second-order differential equation, there's two linearly independent solutions, and you just take like a constant times one of them plus a constant times the other one. And that's what we're basically looking at. We haven't verified that these are linearly independent yet. We will. First, let's try to recognize them. Well, for this we just have to dig into either our memories, if our memories are good enough, or look at a list of power series. There's a couple of things that should jump out at you, like we have factorials in the denominators. In particular, this is an even number factorial and this is an odd number factorial. So where do I see things that look like that? I see something like that here and something like that here. I also see it here and here, but what else do I see here and here? I don't see an alternating sign, like a plus minus plus minus. For us, for us, we would have an alternating sign because this is like a negative to the m. So these coefficients, they're going to have a positive, negative pattern. In fact, this one can be rewritten -1 to the m times 4 to the m, but let me be a little bit more clever. Instead of writing 4 to the m, I'll write 2 to the 2m. Why am I doing that? I guess I'm doing that just to make this match with this. And then similarly, this one is -1 to the m, 2 to the 2m plus 1. What am I doing here? This seems wrong. I wanted this to match this. Well, it does now, but unfortunately what I wrote is not the same thing as the above, right? What I should have written here is maybe I should have just written 2 to the 2m, like I did here, because that was the same thing. That is the same thing as 4 to the m. But I really want this to be the same as this, so I'm going to fix it by just throwing a 1/2 there. Like this plus 1 just gives me an extra 2, and this 1/2 makes it so like that never happened. And right, these are now more recognizable. This one, in fact, let me just do one more thing to show just how recognizable we can make this. Why did I make these the same power? Because I want to lump them together. That's like 2x to the 2m. And yeah, maybe I should draw a line down the middle here because these aren't the same thing. This one is (2x to the 2m plus 1). And now these are looking a lot better. Like I said, we have this negative. This is going to give it an alternating plus minus pattern. That looks just like this. So this one is, whoops, for some reason I started m equals 1 here. There's no good reason for that. But this one is cosine of 2x. And this one is 1/2 sine of 2x. So going back, y was c0 times this one, which is cosine 2x, plus c1 times this one, which is 1/2 sine 2x. So 1/2 c1 sine 2x. Right, and yeah, this is turning into a long problem because the instructions were so long. But, okay, what do we still have to do? We were supposed to find 2 linearly independent solutions. At this point, we can verify they're linearly independent. That'll just take a little bit of work. We have already identified them as elementary functions. The two solutions, just to be clear, the two solutions are cosine 2x and sine 2x. And we have to find their radius of convergence. Okay. So let's do check that they're linearly independent. We can just do the Wronskian. Why is it blurry? Come on. It just went blurry again. What is wrong with you? Are you serious? Okay, I think that's better. Right. What's the Wronskian? I put in the two functions. It doesn't really matter what order they're in on the first row, and then I do derivatives. So this would be 2 cosine 2x and negative 2 sine 2x. I do this minus this, so this would be negative 2 sine squared 2x, and then I subtract this. And of course, sine squared plus cosine squared is 1, so this I get negative 2. But the point is, I did not get 0, so they are linearly independent. What? Okay, blurriness is bothering me. Okay, so we check that they're linearly independent. So for the radius of convergence, here's what we have to do. Recall the ratio test, and this is going back to Calc 2. If the limit as n goes to infinity of the absolute value of the ratio of two consecutive terms of a series, if we call that L, if L is strictly smaller than 1, then the series converges. Yeah, and just to be clear, we're talking about the series just a sub n from n equals 0 to infinity. So that converges if L is strictly less than 1. If L is greater than 1, then it diverges. If L equals 1, it's inconclusive. I won't even write that. If L equals 1, then this doesn't tell you anything. So that's the ratio test. So let's use the ratio test on these series that we got. This one and this one. Okay, so what would we do? We would do L. L would be what? It's the limit as, let's say, m goes to infinity. And then I do the absolute value of the ratio of like the m plus 1 term and the mth term. So this would be negative 4 to the m plus 1 over 2 times m plus 1 factorial x to the 2 times m plus 1 divided by negative 4 to the m x to the 2m over 2m factorial. So I get this mess. It's a fraction divided by another fraction. So I'm going to flip the bottom over. And let me simplify this as I go. X to the 2m plus 2 over 2m plus 2 factorial times, and then I'm flipping this one over, 2m factorial. This should have been in parentheses. Negative 4 to the m, x to the 2m. Right? Okay, now what? Now something cancels. I've got a negative 4 to the m and a negative 4 to the m plus 1. So I'm just going to be left with a negative 4. I also have an x to the 2m. So I'm just going to be left with an x squared. Also, yeah, something cancels here, but let me show you. So what do I have? I've got, first of all, I've got my negative 4x squared. So just from that. Other than that, I've got this on top and this on bottom. Instead of this, let me write the following. Because 2m plus 2 factorial, that would be 2m plus 2 times the next number down times the next number down. So this would be 2m plus 2 times 2m plus 1 times, and then the next one would be 2m, and the one after that would be 2m minus 1. In fact, the rest of it is just 2m factorial, which I can cancel with this, right? So what do I have? As m goes to infinity, this is 0. Right? Because it doesn't matter what x is. If x is just any constant, then as m goes to infinity, because I have m is in the bottom, this is 0. So what does that mean? So the series always converges. Sometimes here you get like, an actual limit other than 0, and then this x would not go away, and then you get some condition on x in order for this series to converge. So this series converges for all x. Because L was always 0, and the series converges as long as L is less than 1. So we would say the radius of convergence is infinity. We say the radius of convergence is infinity if it converges for all x. And yeah, this video is certainly on the long side, but I think I'm basically done. We found the solutions. We verified that they're linearly independent. We identified them as elementary functions. I found the radius of convergence of one of them. Let me just tell you, you can check. The other one also has a radius of convergence of infinity. So you can check this one. Also has radius of convergence infinity. So I didn't do that part. It's entirely similar to this part. But yeah, so let me leave this video at that.